Hello, I'm Peter Wielander, Process Industries Editor for Control Engineering Magazine. And you can see we're here in the basement again for the next of our instrumentation tutorials. In the first three of our efforts so far, we've dealt with first with temperature, then we did 2 on measuring level. So it's about time we get to the third of our 4 main process variables, flow. This is actually a very sophisticated flow meter here in front of me. What we've got is a water supply, happens to be by garden hose, coming to a shutoff valve and then to this straight section of pipe. What you'll see is we have 2 impulse lines connected to our 3051 differential pressure meter. Then there's also this union here in the middle of the pipe, this coupling. And inside the coupling is a small disc with a hole in it that's only 3/8 of an inch in diameter, which is considerably smaller than the inside diameter of the pipe. So what we have done in effect is created an obstruction in the pipe which restricts the flow to some extent but does not stop it entirely.
The concept is very simple. If you place a restriction in the flow, there will be a pressure loss that is proportional to the flow rate. The more fluid you try to jam through the restriction, the greater the pressure loss. So if you measure the differential pressure, you can use it to calculate the flow rate.
What we're going to do then is put water through the pipe at various flow rates and then look to see what the differential pressure is. This is a very common way of measuring flow, and if you listen to some people, it is the most common way of measuring flow in actual applications. The amount of pressure drop across our restriction in the center will be in proportion, theoretically at least, to the amount of flow, and we're going to check that. So right now, with nothing flowing, we're getting a reading which is effectively 0. But let's turn the water flow on and see what happens. So it jumps to just over, right about 18 inches of water with the flow what it is. Now that really doesn't tell us anything because we really don't know what is going through the pipe at this time. So let's try a little calibration. So over here what I have is a nice 2-liter beaker, and I'm going to use the hose to feed into that, and as soon as the flow gets stabilized, we'll use a stopwatch to measure how long it takes to fill the 2-liter beaker, and that will tell us, it will allow us to calculate the flow rate. So let's turn this on and see what happens. Okay, ready, start. There. So it took 13 seconds to fill our beaker. Okay, so now we have one data point to start creating our flow versus differential pressure curve. Let's turn it up and get a little higher reading and then try a second beaker test. So we've opened our valve and we're getting a higher flow, so our differential pressure reading has gone up to just over 37 inches. Well, right about 37 inches. So let's do a second calibration and see what we get when we're at 37. Okay, we're flowing again and we're stable. So let's see how long it takes to fill our beaker. This time it took just over 9 seconds. Now if we want to do this in a real-life situation, we could use this just the way it is. If you did enough tests and you got enough data points, you could create a graph which would give you a very close relationship between the differential pressure reading and the actual flow rate. There are also ways that you can do that through calculations. There is a website, eFunda, Engineering Fundamentals, which gives you a very nice calculation based on the differential pressure and the various diameters that are involved.
There are many advantages to this approach. It's a simple technology with no moving parts. The flow measuring sensor can be very compact. Depending on the configuration of your pressure sensor, you can set it up for bidirectional flow. The approach is scalable over a very wide range of sizes, and it's relatively inexpensive. Of course, there are drawbacks too. It has limited accuracy and turndown range. If high precision is your primary objective, there are probably better technologies. The orifice causes a pressure drop and reduces the pipe's free passage. As sensor technologies go, this is one of the more invasive. Ultimately, accuracy and turndown are related to pressure drop. In other words, the more accuracy and range you need, the greater pressure drop you'll have to tolerate. The orifice is prone to wear. While there are no moving parts, the orifice itself is often a wear-prone point due to the high liquid velocity. If the orifice gradually enlarges with wear, the flow measurement will read low. On the other hand, if it becomes partly obstructed with debris, the measurement will read higher. The same application and installation guidelines for good pressure sensor practice apply here. Anything that interferes with the pressure readings, such as clogged impulse lines, will interfere with the true flow calculation. Changes in liquid characteristics, including viscosity, multi-phase flow, and even temperature, can affect readings. Of course, these are generalities, so discuss your specific application needs with any prospective suppliers.
Thanks to the nice folks at Rosemount and Emerson Process Management for giving us the sensor. So for Control Engineering, this is Peter Wielander, Process Industries Editor. Thanks for watching. Visit our website, www.controleng.com.